So a ladder AB of mass M and length 3A has one end A resting on rough horizontal ground. So here's my rough horizontal ground. Here's the ladder. That's A. The ladder is resting on that horizontal ground. It's rough. So here's my normal reaction. I'll call it R. And my friction would go this way. So mu R. And scanning the question, it says it's got an angle of 60 degrees with the ground. So this angle here, 60 degrees. I'm going to extend that a bit just to give you a bit more space. This is ladder AB. The other end rests against a smooth vertical wall. So here's the wall. It's smooth, so there's no friction. So I don't need to put any friction. If it was rough, then friction would be in this direction. But we know, that's because gravity and generally would be trying to force the ladder down. The friction would be resisting that motion. However, that's not needed because it doesn't say any friction. But just because there's no friction doesn't mean that we don't have a normal reaction force. This time I've called it M. The ladder is modelled as a uniform rod. It's got a mass of M, a length 3A, so 1.5A either side of our weight, which is mg. A load of mass 2m is on the ladder at a point C, where AC is A. So if this point is C, we have 1 meter. So 1A. Sorry, 1A here. To get to C, we have a mass of 2m, so we have a weight of 2 mg. Then, that is all the information from the question. Find the coefficient of friction. It's in limiting equilibrium as well. So all of the moments and the resolve forces are going to end up being 0. So first things first, I'm going to think about resolving forces horizontally or vertically. It really doesn't matter. But if I think about horizontally, the only forces I have in this direction are mu r and minus m. That's going to equal 0. So mu r equals my normal reaction force. Okay. Then if I think about vertical, so I have vertically r, and then vertically downwards, I've got 3 mg in total. So therefore R is equal to 3 mg. That's nice. Now I can think about moments. All right. So at this point here, I still have plenty of unknowns. But I do know that my R is now 3 mg. And this is going to be 3 mu mg. So the only unknowns I've got now are my mass m, my length a, and my coefficient of friction mu, because r is now replaced and n is replaced as well. So if I think about moments about, and I'm specifically going to choose moments about A, because then I can ignore 2 of my forces, and it just makes it generally easier. And I know there are lots of unknowns, but let's just do moments about A, because then I can get rid of my R and my mu R. I can just focus on my weight, the mass that's at C, and the normal reaction from the wall. So moments about A. So when I do that, you can see I've got this triangle here. This triangle here is going to be useful. And this triangle here is going to be useful. So those 3 triangles. And all with this angle here being 60 degrees, which we already had earlier on. So when I think about my moment about A, I think about this force here, the 2 mg. The perpendicular distance from A is this line here. So that line there is going to be 1a multiplied by cos 60, using normal trigonometry to get that perpendicular distance. And then the force itself is 2mg. That's clockwise. So we've taken this clockwise right now. Then we have another moment with our mg here. Well, the perpendicular distance there this time is going to be 1.5a times by cos 60. And that's going to be multiplied by mg. That's also clockwise. And then we have an anti-clockwise moment here. Well, that we've already got here is 3 mu mg in total. The magnitude of that force. But the perpendicular distance of that force from A is going to be this line here. And because this is my anti-clockwise force, and moments are in equilibrium, they're going to balance each other out. So those first moments are going to equal my classical distance there, which is going to be 3a sine 60 multiplied by 3 mu mg. Now, I want to make things a little simpler at this point. I can see cos 60 is a half, and then I've got times 2. So half times 2 cancels out. Then I have cos 60 times 1.5, so that's 3 over 2. So, well, I'll just make this 3/4, not forgetting the a that's in here as well. And then sine 60 is root 3 over 2, so I'm going to make sure I include this in my calculations. Root 3 over 2. So if I write all of this out in a little bit simpler, I've got 1a times mg, so I've got a mg. Then I've got 3/4 a mg, so plus 3/4 a mg. And then on the right-hand side, I've got 3a times 3, so that's 9a times mu, so 9a mu mg. So 9, I've also got root 3 over 2, and then it was a mu mg. At this point, you can see every term has m, every term has g, and every term has a. So this just cancels out to 1 here. So I've got 1.75 equals 9 root 3 over 2 mu. So I could do 1.75 divided by my 9 root 3 over 2 to get me a value for mu equal to 0.2245, which is 0.22 to 2 significant figures. To state how I've used the assumption the ladder is uniform, to word this carefully, it would be to say that the weight goes through the center of the ladder. So when something is uniform, the weight acts through the center of the object. So in this case, the center of the ladder.